Thank you, Martin. Thank you, Martin. That's very kind words. So let me just see. Right. So this is working, I'm hoping.
Yes, it is.
Everybody can hear me and see my screen. Okay, thank you very much for having me. When Martin asked me to give this talk, I was quite excited about all the stuff I could fit into a seminar on GID dynamics before and after the MPT. But I realized, given the time, I'm going to have to limit myself to glacial terminations and transitions into a glacial state, both before and after the MPT. And then I'm going to finish with what I think are some interesting open questions for the ice core community and generally anyone interested in the MPT. Given the shortness of this seminar or talk, I'm going to rely on your background knowledge to some extent, but I've referenced figures throughout my talk, and then welcome to go back and look at the recording afterwards to fill any gaps that I may leave. And I've also listed a bunch of our recent papers at the end of the talk, which relate to the questions that I'm going to ask. Okay. So in terms of what we might be interested in across the MPT, in particular, the difference between the 41,000-year world and the 100,000-year world. As we all know, the glacials of the 100,000-year world were characterized by bigger ice sheets, lower atmospheric CO2, and probably enhanced deep ocean stratification with respect to glacials of the 41,000-year world. And this deep ocean stratification question really does kind of relate to what may be causing atmospheric CO2 to be lower during 100,000-year world glacials. So just as a brief introduction, we know that orbital forcing did not change across the MPT, but obviously the Earth's climatic response to it did. And the higher amplitude of GIG variability in the mid to late Pleistocene necessarily requires greater amplification of the orbital forcing that we receive, i.e., that is, non-linearities within the climate system must play a more important role, more substantial role during the 100,000-year world. And this itself implies that the mechanisms of glaciation and deglaciation somehow changed across the MPT, and that's what I want to talk to you about today. So I'm going to start by talking about glacial terminations, and these ideas have been around for a long time, papers including Broker and Denton in 1989, and then probably most famously by George Denton and others in 2010. This is the idea that abrupt variations in ocean atmospheric circulation can provide feedbacks with respect to atmospheric CO2 and global temperatures to amplify the rather modest insulation forcing that we get across a deglaciation in order to provide or explain the large magnitude of change that we get across a deglaciation. So we receive an increase in northern summer hemisphere insulation, mostly as a function of precession. This somehow leads to a reduction in ocean circulation, or the aim during early deglaciation. This itself may cause CO2 to come out of the ocean, and at some point CO2 or global temperatures reaches a sufficient level that we have an interglacial. We come into an interglacial. It's not just CO2, of course, that can feed back. Temperature is also an important player, and I've just mentioned a paper by Gregor Knorr and others where they do hosing experiments starting from various background states, including interglacial and pre-subglacial. When they start with the glacial state, where we have rather enhanced salt stratification in the deep ocean, they get a much larger temperature response over Antarctica as a function of this collapse of the AMOC. So again, what's kind of important here is the idea that we have enhanced stratification of the glacial deep ocean, which could help to store CO2 during a glacial period and release it during deglaciation. But also this enhanced stratification, which could reflect enhanced salt stratification, does actually allow a relative warming of the deep ocean, which can provide this additional boost of warming during what we might call a Heinrich-Stagel event, or a terminal Heinrich-Stagel event, which would be the end of the ice rafting associated with the initial collapse of the ice sheets. So that's the idea of a seesaw-driven termination, and that's termination one, so the last deglaciation. And of course, we've got studies that enable us to go back through time. This is an indirect approach using speleothem records. So this is terminations 1, 2, and 3, and these have been published by Hai Cheng and others in 2009 and 2016, which shows if we have an indirect approach, the monsoon records suggest we have a weak monsoon event, which would be synonymous with the weak AMOC event during deglaciation. At the same time as these weak monsoon events, we see that atmospheric CO2 is going up, rather the same as it does during termination 1. A more direct approach, and this has been identified by Roberts et al. And Dini et al. In terms of neodymium records from the Northwest Atlantic, which shows this relationship between when we have more southern source deep waters during a Heinrich Stadial event. This is again Heinrich Stadial event 11, which is the same as this according to termination 2 in the monsoon records, during which CO2 will come out of the ocean. And at some point we have recovery of the AMOC and we have the start of the interglacial. So these are two approaches to go back in time. And then going back for the full 800,000 years, we've been working on developing records from the Northeast Atlantic in terms of ice rafting and the abundance of polar species as a temperature indication. And here I've also plotted a prediction that we made back in 2011 of what Greenland or abrupt climate variability might look like based on an algorithm designed around the Antarctic temperature record. Now, I know many of you in this community will have seen this, and some of you didn't like it at the time because it's not really a record, which is why we invested about 10 years of time trying to sort of create this in an ocean proxy perspective. And I think we've shown that it's not a bad representation of what abrupt climate variability does look like over those 800,000 years. So importantly here, we can see that every termination is associated with what we call a terminal ice rafting event. And again, this reflects perhaps to an extent changes in insulation driven by precession in the north, leading to, amongst other things, collapse of the ice sheets and fresh water, which affects the AMOC. So during these very icy events, we see that atmospheric CO2 is going up. And this is kind of a ubiquitous solution, or at least a representation of what goes on every time we have a termination. So I'd like to just define the termination or the deglaciations of the 100,000-year world as this reproducible sequence of events that involves changes in insulation, changes in ocean circulation, and a corresponding increase in atmospheric CO2, which leads ultimately into an interglacial state. Okay, so this would be the kind of characteristic glacial termination of the 100,000-year world. So then the question arises, what did these look like before the MPT? Did we have deglaciations, glacial terminations in the same way that we have during the 100,000-year world? Okay, and just as a very brief interlude, and I can't talk about this paper to any great extent because we don't have time, but there is a preprint available on Earth Archive if anyone would be interested in going to have a look at that. It's a paper under review at the moment. I'm semi-hopeful that it might be published by the end of the year, but I don't know yet. But anyway, just a little abstract from one of the findings of that paper, and this is not a controversial part at all, is that glacial terminations of the 100,000-year world are related to, or are driven essentially by precession, but in conjunction with rising obliquity. So if we look at these points along the top of this graph here, the purple circles represent every precession peak of the last 800,000 years. And by precession peak, I mean a minimum in the precession parameter, which gives rise to a peak in northern summit intensity. And what I've picked out in green here, and I've labeled candidate precession peaks, are those precession peaks which begin while obliquity is increasing. And it means that whenever we have one of these candidate precession peaks, you basically have the simultaneously warm summers due to a combination of precession and obliquity. Now, when we look at the subset of these candidate peaks that are associated with glacial terminations, and by the way, it doesn't matter which age model we use to select these precession peaks, we select the same set for every termination, depending, irrespective of the age model we use. If we look at these subset of these candidate peaks associated with terminations, there's these stars here, and we can see that, for example, T3, termination 3 here, the precession peak is just after the maximum in obliquity. So if time is going this way on this plot, the precession peak is when obliquity is dropping, but it's still relatively high. And so you can see all of the terminal precession peaks correspond to a moderate to high values of obliquity. If we go back to the beginning of each of those precession peaks, so when it starts to warm, when northern summers start to intensify, you can see that they all correspond to an increasing obliquity signal. So the point is that you need both precession and obliquity for glacial termination, but they're actually driven initially by precession while obliquity is rising. So the reason I was telling you this is because these candidate precession peaks are quite important. Every one of the terminations is associated with a candidate precession peak. Right, now back to the main talk. Okay, so here's some examples of 3 terminations during the 100,000-year world, which you should be fairly familiar with. And the records I'm showing here, 3 actually, are from David Hodell's work on U1385. That's the Iberian margin. So we have the benthic 18 record in red here, and then we have the benthic C13 record down here. And of course, that's some sort of proxy for overturning in the Atlantic. So you can think of it as a first order AMOC proxy. So we have these negative events here would be associated with reduction in the AMOC. And this is the Planktic 18 is some sort of temperature proxy. And then the yellow is our IRD, so ice rafting record from 983, ODB 983 from the Northeast Atlantic. And from the same core site is our record of polar species and flora. So we can see during these terminal ice rafting events, which are all associated with candidate precession peaks, we see the increase in insolation, which is related to an increase in ice sheet melting. And we have an increase in ice rafting, which represents the breakdown, the breakup, the catastrophic demise of marine-based ice sheets in the Northeast or the North Atlantic. And that's also associated with these a reduction in the AMOC. And we all know that atmospheric CO2 is coming up at the same time as those events. So that is, what I've been talking about, these canonical terminations of the mid to late Pleistocene. So now I'm going to show some records from the 41,000-year world. Most of these were published back in 22. The red record here is actually not published, but because MPS is not present in the North Atlantic during this interval, this is just the accumulation of other species, so non-polar species in the same core site. So again, the same records as I was showing in the 100,000-year world, but now for the 41,000-year world. The question is, what were deglaciations like? Were they canonical terminations? Let's first of all look at marine isotope stage 37. So it's 1.25 million years ago, which is just before the MPT. So it's well within the 41,000-year world. Okay. And you can already see that it looks a little bit like a termination from the 100,000-year world. So if we start with the precession increasing or decreasing, the parameter decreasing, and we have a candidate precession peak here, we have ice rafting, we have cold temperatures in the North Atlantic, and we have this subdued AMOC, which might be reflected by this C13 record. So this looks, to all intents and purposes, very much like a termination in the 100,000-year world. Now we look at stage 41 and 43. Now, the minima in the benthic 18, again, is associated with a candidate precession peak, like you might expect. However, this time, the terminal ice rafting event, while they are associated with the precession peaks or precession minima, these are not candidate precession peaks, but these are the last episodes of ice rafting associated with these glacial periods. So they're terminal, but they're not terminating. They're not deglaciation. So the question here is, what was CO2 doing during these events? When did CO2 go up? If it went up during the deglaciation, did it go up in time with the AMOC event like it would do in the 100,000-year world, or was it delayed? What was Antarctic temperature doing? Because we remember back to Shackleton 2000's paleoceanography paper, the whole point of this record, going back to the Iberian margin, was that the benthic 18 record looked rather like Antarctic temperature. But there's nothing here, as you can see in stage 42 here, during this major ice rafting event, there's no change in the benthic 18. So the big question for me is, what's Antarctic temperature doing across that interval? And I think this is a prime target for beyond Epica. Okay, that's deglaciations. I'm afraid it's very brief, but now I'm going to go on to transitions into a glacial state. And again, this is all work that we recently published in paleoceanography in 23. So I'm going to have to go through this quite quickly, but please feel free to ask questions or go and read the paper if you'd prefer to do that. But basically, in this paper, we're trying to make a case. So we've seen a lot of work about the interactions between millennial scale variability and orbital timescale variability during deglaciations. But we're now interested in the transitions into a glacial state in this paper. So if we just look at the last 100,000 years, we all know that DO19 and DO20 were very large events. You can see here that within the O18 record from Greenland, if you look at a histogram of the magnitude of all the DO events, DO19 and 20 really sit right at the upper end of that, of the magnitude of DO warming across the last 100,000 years. So it's beyond 2 standard deviations from the mean. But it's not just temperature. The dust records from Greenland also show DO19 and 20 being very large. Temperature records, SST records from the Iberian margin have DO19 and 20 up in the upper 25% of all events. And again, if we look at speediotherm records from Hula Cave, and that 19 and 20 are again some of the biggest events that we see of the last 100,000 years. So we see the very large amplitude of DO variability across stage 5-4. And in the paper, we argue that this is probably reflecting high amplitude AMOC variability, although we don't have well-resolved enough records of real AMOCs reconstructions to be able to show this for the real ocean mixing, if you like. In terms of Antarctica, DO19 and 20, right, the cooling across Antarctica associated with DO19 and 20 is very large magnitude, obviously, but it's also faster with respect to its duration than many of the smaller events. So it was actually quite a special set of circumstances in Antarctica. And if we go to Antarctica now, I don't mean today, I mean this slide, and we look at the last 90,000 years. Sorry, my dog is fussing here. This is the Antarctic temperature record, as you all know. This is the millennial scale component. If we look at a running window of standard deviation, so I've taken 7,000 year smooth and or looking at standard deviation of a 7,000 year interval, and we can define glacial periods as kind of periods of quiescence with respect to millennial scale activity. So we know that millennial scale activity is less pervasive, less pronounced during full glacial and full interglacial conditions. And we can see that if we draw a threshold at 0.4 or 0.5 in the standard deviation, the running standard deviation of Antarctic temperature, the interglacials and the glacials sort of stick out as these periods of relative stability. And we can see that if we do the 800,000 years with the same thresholds, you can see that the glacials are stable, the interglacials are stable. We kind of think of this as glacial stability reflecting enhanced stratification in the deep ocean. And the reason I'm showing you this is because what we quite like to know is there any systematic relationship between the occurrence of these very large amplitude DO events that go into stage 4 and the appearance of stability in the glacial ocean. And so if you look at this plot here on the left, this is the millennial scale of component of the Antarctic temperature record, and these are the abrupt or rapid or large scale warming and cooling events associated with the major Antarctic warm intervals, the millennial scale warm intervals. And these AMO, AIM 1, 2, 3, 4, and Antarctic 1, 2, 3, 4, 5, 6, 7 are from the literature. I haven't made these up, but we can pick out every one of these warming events using a very straightforward smoothing approach. And importantly here, A5 and A6 would be DO19 and 20. And then we can look at the last 800,000 years and work out, well, if these events didn't play any role in the transitions to a glacial state, if they were just a symptom of being in a let's say a bimodal state, then we wouldn't expect any systematic behavior or relationship between whether it was cooling or warming prior to the appearance of stability. And what we show in this plot here is that these are all the warmings and the coolings in terms of these very large amplitude Antarctic events. And every one of the transitions to a stable climate regime is associated with a cooling event, a strong cooling event over Antarctica. So in summary of that, basically we envisaged that the transition to a stable state, a stable glacial state with respect to millennial scale variability was a result of a strong mode of the AMOC associated with this strong cooling over Antarctica just prior to that stable regime.
Even 20 minutes.
I've had 20 minutes. Oh, okay. I'm not far off, actually. Oh, but you're counting that introduction, aren't you? All right. So if we look at, and those of you who've looked hard at the Antarctic records will know this already, but occasionally CO2 is decoupled from Antarctic temperature. In particular, it's decoupled across stage 5-4 here. And you can see that within stage 5-4, we have 19 and 20, and CO2 is held up across the year 1920 and then drops into stage 4. And if we plot the difference between CO2 and Antarctic temperature over time, we can see that these windows of decoupling, which I've shaded in gray, are always associated with the transition into a glacial state. They're also associated with high amplitude millennial scale variability. Now, what you notice here, if you look at the histogram with respect to time, AAT is just a regular distribution here with only one mode, whereas we have the appearance of bimodality in the histogram of CO2. And this blue window here is not actually picking out the minimum in the distribution. It's actually the maximum in millennial scale variability observed at site 983. All right, so it actually coincides with this minimum in the distribution. So what we suggest is this decoupling, which is a response to amplified DO variability, is actually resulting in decoupling between CO2 and Antarctica. So CO2 is held up during this window of decoupling and then drops into the glacial. But it's not just CO2 that shows this decoupling. So just focus on this line of plots here. This is Antarctic temperature, the histogram. This is the bimodal distribution of CO2. But we also see the appearance of bimodality in O18, in dust, in Iberian margin SST, and in North Atlantic temperatures. And this maximum we see at the same time as the minimum of the distribution is reflecting a maximum in the millennial scale variability seen in the Northeast Atlantic. And the same blue period intervals are also the periods of enhanced decoupling between a range of parameters in Antarctic temperature. So this describes sort of the relationship we see over the last 800,000 years. When we go into a glacial, we see enhanced millennial variability. This gives rise to decoupling. And we think that that's associated with the transition to a glacial state. Okay, so what about prior to the MPT? The question is, we don't have CO2 records or Antarctic temperature records, but we do have records of benthic O18, of course. And so if I show you the running sort of modal distribution through the last 5 million years, this is the bimodality in O18 that I've just shown you for the last 800,000 years. But the bimodality emerges across the MPT. So prior to the MPT, there is a unimodal distribution of O18. And this bimodality, which we argue is related to the influence of millennial scale variability during the transition to a stable stratified ocean, was somehow different prior to the MPT, i.e. it implies that millennial scale activity did not drive such a decoupling between benthic O18 and CO2 versus AAT during these transitions. So it sort of implies that dynamics of IG to interglacial to glacial transitions somehow changed across the MPT. So now just to summarize of all of the stuff I've just been saying and then invite some questions. In terms of deglaciations, my sort of questions to the ice core community would be, how did Antarctic temperature and atmospheric CO2 and other greenhouse gases respond to AMOC perturbations before the MPT? Were deglacial changes in atmospheric CO2 and, for example, mean ocean temperature approximately in phase with ice volume before the MPT, or did they care more about the abrupt AMOC transitions? And in terms of IG to G transitions, how and why were the interactions between millennial scale variability and the development of glacial conditions, i.e. enhanced stratification, different for the MPT? Was CO2 decoupled from Antarctic temperature during those transitions? And could this change in the interplay between millennial and orbital timescale variability help to explain perhaps the shift to lower glacial CO2 across the MPT as we see that shift to more stratified deep ocean during 100,000 year glacials? And here I've just put some papers up that you'd be welcome to go and have a look at. But that's me done. Thank you.
But you have to the last 5 million years, maybe also a little bit to see what's really going on during the MPT. Sorry. Can you see something? No, I have to enlarge it. Is that fine?
Actually, now we see your two slides, side by side. Maybe you can swap the display.
I see both now, but you see only one, or?
We see both as well.
Or is that possible? I have to go to this other screen. And now?
We still see both displays.
I'm sorry, it worked for me. Just tested it. Sorry, I will take off this here. Zack. And then now I will unshare and share again. Let me see. Sorry for that. With two screens, there's always something happens. Unpredictable. And now it's one?
It's perfect now. Thank you.
Okay, sorry for that. Yeah, so I would like to talk about the results from not so recent anymore, but still 5 years ago, expedition 3x3 within the IODP project with joyous resolution. It has been led by Gisela Winkler from Lamont and myself. There were quite some people involved. I don't name everybody here. There are some people mentioned here that were kind of the core group for this long-term study over about 5 million years. But there are also many others, all the shipboard scientists during the leg, and of course all others that came to us working on the sites after that. So that's still ongoing work. And this is kind of the first shot over showing you the variability of the ACC over the last 5 million years. So as an introduction, I think maybe don't have to tell that here. The ACC is one of the most important probably current systems in the world ocean. It flows around Antarctica and links all these different processes here between the lower latitudes, the higher latitudes, Antarctica. It also distributes into the different ocean basins that you can see, both deep and shallow circulation. So everything is kind of connected here, and it's probably, I think Steve mentioned that also, it's a kind of important for the atmospheric CO2, the Southern Ocean. So there's the North Atlantic, but also and the Southern Ocean is probably more important from quantitatively, at least in the more recent times. And it may impact also the global overturning circulation, and also finally also the Atlantic meridian overturning circulation, like from the south. So the impact is probably not only from the north, but also from the south. Yeah, this kind of anecdotic view here, that was our great honor to go for the first time to the South Pacific. You can see here all the IODP drillings over time since the 60s when the deep sea drilling project started. You see here, these are our little dots here. So we had like 6 sites. It was a large effort, not only to drill these sites, but to get the data, to get permission to drill. You need seismics, you need preliminary course, and that was a process took 10 to 15 years. But in the end, we were there. As you can imagine, the weather is a big issue. We originally wanted also to have a transector, like similar to the well-known LEC 177 transect across the fronts. We were not so much able. We were mainly staying in the subantarctic zone, but you will see subantarctic is also nice. Important processes happening there. And that was because of these weather issues. That was a big deal during that cruise. Could also say was a nightmare in the end. We were quite successful at the beginning, but then there was this kind of pressure system coming here, covering nearly a big part of the Southeast Pacific, and we had to escape and then come back and lost like 2-3 weeks. So that was a significant part of the time we could not drill southern sites anymore. There was another. But in the end, I don't want to complain. It's difficult, but one day somebody has to go back. There are still many sites that have to be useful. Let's hope that we get something IDP similar in the future. So here I look at this ACC itself and the sites that I want to discuss mainly here. And these are the 2 central South Pacifics. They're right here in the subantarctic part where you have the major currents slightly north or at the subantarctic front, 1541 and 1540, both going back to the Pliocene. And then because this transect was not possible with the IODP drilling, we used also some other cores previously drilled or cored that go across the front. So these 3 cores in order to show that what we are seeing here in the subantarctic is something that is more also maybe similar or not to the more southern part, let's say up to the polar front or even beyond the polar front. And what are we really, what's the proxy here? We are trying to analyze or to reconstruct the ACC. And what we are using is a bottom current that is like registered in the deep sea sediments in the sorting of the grain sizes, the sortable silt, so-called sortable silt. And you see here some examples here across the front of the hydrography, and only look at this subantarctic front. There's a northern one here, there's several branches. Polar front, you see how these currents go to the deep. This is only 1,500 meters, so we are much deeper, 3,500 about. But this extends to the bottom of the sea, and actually the ACC is the only area where the currents really go from the surface to the deep ocean, so we can use the deep sea, this deep sea records of grain sizes also as a representative proxy for the current speed of the ACC, also in the shallow or even at the surface. So that's the approach. And we use classical sedimentology, this so-called sortable silt. McCabe kind of started with this already in the 90s. There's a relation between the sortable silt and the flow speed that is different in different areas, but it's always nearly linear. So maybe the absolute values of what we reconstruct in flow speeds are not correct, but the trends and the fluctuations are, of course, are all right. And then we used to extract that from the record, and it's not so easy to do this in the Southern Ocean because all the sediments are full of opal, at least in glacials, and opal is not so easily to resolve because we want to have the sorting of the terrigenous particles, which are only a relatively small part. And that's why it's a large effort to do this discrete samplage, the dots here, which we managed to do. There are some errors here involved, but if you compare to the red curve, which is zirconio-bidium ratio, it's not actually seen, it's already calculated in sortable silt mean. You can reconstruct it. We use it to calibrate actually zirconio-bidium form, and you can use it with an XRF core scanner in order to get high resolution. So you have like every centimeter about across 150 meter sediment depth, which would never be possible, of course, with really single measurements. So that has been shown in other places. That's okay, I think. The correlation could be better, but that's because of this pelagic location. If you go continental march, it's much better. But that's we cannot change it. I think it's still in the direction should be, of course, okay. So as I said, I'm talking about different time intervals. So MPT is a topic, but mainly not the main topic here. I would like to start here with the younger parts, the mid to late Pleistocene, 100 cycles, to compare also to the shorter course, what's going on here on the glacial interglacial. Then I will come to the Pliocene and look a bit into the MPT in between. I'm sorry, there's a telephone. Okay. Yeah, this is now here a different course here. This is what I said, this transect here of sediment course. You see this Polarstern course from the polar frontal zone across the polar front into the Antarctic zone, and then attached also the two. They are not at the same transect, but they are transferable because they are north of the subantarctic front, like subantarctic zone records, the two ODP side. This time only the uppermost part, the last three glacial interglacial cycles. On top, you see the ice core data that you're probably very familiar with. And you see that if you look only at the orbital scale variability, there is an overall pattern that is really consistent, even though you're in different places here. So it's in all the places, it's the case that the ACC, so this is here calculated relative to a Holocene mean, is always relatively strongly, partly even half during glacials, and it's much higher during the interglacials. If you look in detail in these different curves, you see that the southernmost core, this violet curve here, it has also this pattern, but the amplitudes are much smaller. That means that here, if you go to the Antarctic zone, you still have the same sign, but you have a much subdued glacial interglacial variability. And that comes probably also, I'm not showing here, because the frontal movements that are also involved. So we think that there's an overall ACC fluctuations across the whole zones, but it's attenuated in the subantarctic zone, amplified. The variations are strongest there. Yeah, now to the MPT already. And this is here now showing again what we've seen already before in the previous talk is benthic data from the Leseki-Raybaum stack, then the CO2 record from the ice core EDC. And this is now our two sites here, west and east of the East Pacific Rise. I'm getting back to this later. They're really amazingly similar. They're still about, I don't know how much that is, 1,000 miles away or so. They're really amazingly similar. And what I see is a clear increase already in ACC strength a little bit before the MPT really starts, before stage 31, marine isotope stage 31. And then you have during the MPT, and also afterwards, you have very strong glacial interglacial fluctuations. that really sometimes the interglaciers reach 150% of the Holocene value. So if compared to glaciers, that's a doubling or even more. And then after stage 11, in this case, you have then a lowering of the amplitudes. So it's kind of different from the common pattern. What is also interesting, this record here is, I cannot see it here now. From the Drake passage, there's another core that reaches this kind of MPT time frame. It's directly at the entrance, directly at the subantarctic front. It has a slightly different pattern. There's an early increase, but it's more consistent, and the fluctuations, the amplitudes are more, let's say, stable throughout the interval from the late MPT to the present. So that's something was to figure out what that really means. And one idea is that this part here, what is going to the Drake passage, is something else than this here, because some of the currents we know that from the present oceanography is moving towards the north into the Humboldt current system, Peru-Chile current system, and not everything goes straight on here towards the Drake passage. And that's might be the reason to look into also records further downstream, let's say from the Humboldt current system towards the tropics. I think the strength of these sites in general is that you have also close link probably to the tropics. In the Eastern Pacific, you have this northward movement of water masses. And in fact, you see, if you look at these ODP sites here, older ODPs than the Peru upwelling, and also here in the eastern tropical Pacific cold tongue, that they all show a kind of cooling already starting more or less, let's say, at least here the cold tongue, at the time when we have this increase in the ACC. So there might be a connection between the ACC development in the subantarctic and what initiates the cooling that's happening in the cold tongue. And these things are probably also related to large-scale variations between tropical Pacific, probably also involving long-term variations of El Nino and other processes, and the subantarctic. Yeah, I don't want to talk much about opal. There's also very interesting opal fluctuations. Opal is always higher during glaciers. That would mean that you get the polar frontal zone further to the north towards the subantarctic, higher opal contents. But the patterns are sometimes also deviating from the grain size. So there's, for example, an opal belt shift quite early before the MPT. Yeah, that maybe that's from a talk in GU this year. Maybe somebody was there. I don't want this summary again of this. What's going to happen with the ACC at the MPT or before, and if this is something to do with the CO2 based on the proxies beyond the ice cores. For example, this one is also discussed, I know, the Liefwerk-based CO2. There might be that you have some enhancement of the interglacier related to the ACC, but that's very speculative. We need your data from the oldest ice to really say more about what's happening to the early CO2. Yeah, that brings me now to the long record itself, and that's what I already mentioned before. Here's the 5 million years. And the first amazing thing here is really that both the blue and the red curves from both sides here, 1541 and 40, they are really so similar. You have to consider that there's this East Pacific rise, a major obstacle in the flow of the ACCs in between, and it's just flowing over it and recording the same thing in both sides, except maybe for the Pliocene, where you have stronger currents. On the red one is the 1541 on the western side of the ridge than to east, but that's a different story, I think. So that's amazing. And the second thing that amazed us also when we submitted the paper, that you don't have the classical picture of Pliocene stable, like more stable climate, and then towards glacial conditions towards the northern hemisphere glaciation, early Pleistocene. We don't have that. We have a kind of baseline. This is the Holocene level again. That's not so different all over. Maybe slight trends here, but there's this very strong fluctuations on long time scale. Now these fluctuations, I will have a figure in a second. They are mainly modulated by 400,000 kiloyear cycles. So that's more than glacial interglaciation. And these 400 kiloyear cycles, they are particularly evident during the Pliocene, which is kind of unexpected considering that the Pliocene is thought to be more stable. That's why that was in the major discussion of our nature paper earlier. Well, how can we explain these things here? So here you see now this black curve is like a multi-million year trend that we observe in our data compared to the Holocene level. You see there is an increase towards the Pliocene, maybe culminating shortly before we enter into the Pleistocene, Northern Hemisphere glaciation, then going down, and then there's another minimum like prior to the mid-Pleistocene transition. And this is kind of opposite to the enhancement of the gradients. These are SST gradients between the tropical Pacific and mid-latitudes, and east-west also across the tropical Pacific. They increase for the Pleistocene. That would, at the first glance, would mean that you have an increase also in ACC strength, which we do not have. And right here, other proxies, ice volume modulations, model results. Undrill is somehow also fitting to kind of, when we have a stronger ACC, you have a open marine conditions, so reduced Antarctic ice sheet most likely. But it's of course very difficult to compare this in detail. But let's say the overall fit is there. That would imply that we have really here this maxima, probably also the maxima in like ice sheet we treat in the Western Antarctic ice sheet. Yeah, this nice figure here. Maybe if you want, read the picture, the paper. It's kind of complicated, but our idea at the moment is if we go just from early Pleistocene to the late Pleistocene and then to the early Pleistocene, that we have different processes, low and high latitudes, that kind of counteract in parts also, and that the westerly winds, of course, play a role. They increase during the beginning because temperature gradients increase. But at the same time, the ice sheet and sea ice and density development around Antarctica was kind of not so much developed, and this later on controlled then the decrease because of this density gradients. They decrease actually during the early Pleistocene. So this is an explanation why that goes further down and not further up, as one would have expected from temperature, atmospheric circulation forcing. And this is only one part. There are then also many other processes involved. For example, also the monsoon system is most likely affecting, as is known from many paleoclimate studies, also on shorter time scales, that it's affecting the westerlies and also then probably affecting the ACC. And there's this increase here during the Pleistocene, kind of paralleling the long-term trend here. This peak is a bit too late now, but there is a peak also there. That's probably fine. That's the question: is this, how is that even tectonic influence that has been still discussed? It's not clear. I would say it's a Tibetan plateau uplift responsible, and then also even influencing here the ACC. And then there are also changes in North Pacific circulation. There's a kind of opposite pattern between our subantarctic opal deposition and the PMOX circulation, Pacific Meridian orbitonic circulation, that was active during the Pleistocene in the north. So these things can also affect the ACC strengths, of course, and in the end, on the long term, there are also nice proxies for the sea ice extent and the opal deposition close to Antarctica. This is really a coastal site. It's not here somewhere. Oh no, it's here, Antarctic Peninsula. You see that it decreases, sea ice increases then abruptly into the early Pleistocene. That affects then here the density gradients. Yeah, I think, yeah, that's nearly towards the end. This is what I mentioned, this 400,000 kilo year cycles, which are paralleling somewhat eccentricity. This is the adjusted filter with 413 kilo year. It shows here our ACC strengths, and the gray bars are always like maxima of the ACC, and you see they fit mostly to this in the data, of course, to the maxima, which we call here plyo 1 to 3. And it becomes then more difficult, let's say, more subdued here during this early Pleistocene, and then increases again in the middle Pleistocene. And these changes are somehow consistent also with Antarctic ice volume as in the modeled and Asian monsoon, at least in parts, also with the 13.3, but these changes are not so clear. They seem to be in phase with the 13.3, the global stack, but then during the late Pleistocene, that's changing. So the question is, what are these 400,000 year cycles? And our idea was that this is also related to kind of modulation of the precession cycles. As Steve mentioned before, precession is always a good solution. In this case, makes sense because we know from more recent records that the precession affects the tropical Pacific and also the distribution of the configuration of the westerlies, and that could also be then translated again to the ACC. And this is all things that are only valid in the South Pacific, and they are different in other ocean basins. I think that's something for the future. And it comes out already in many some records that the Pacific has its own functioning its own scheme compared to Atlantic and Indian Ocean sector. Yeah, that brings me back to our link here to the EPICA V1C. This is already an older figure. That was here again our sites, and what I'm not showing today here, there are other sites. There's a second, the 1539 is a bit further south, but this is really high resolution. It has 300 meter sediment covering 1.3 million years, and that's the time range of the oldest ice probably. And we are now starting a project, and others, also Chandranat and others from the US work on this record. It has really the potential also to look into sub-millennial, sub-orbital, sorry, millennial, not sub or millennial, being even that, but in an open ocean site, just in the middle of the Pacific, you get storm changes in opal content, but you can get surface temperatures. You can get something like Antarctic temperature if you assume that the surface temperatures in the subantarctic Pacific, that they are really similar to what we record in the Antarctica, which is of course more complicated, but at the first glance, this is a possibility to get high resolution records. In addition to those more coastal sites where we had already some people, among Sonus, working on one site here, and Steve is involved there also. They have also 800,000 years of millennium. But this one here has 1.3. I think that's a really good site to compare with EPICA records. Thank you.
Thank you very much, Frank. So we're running a little late, so we won't stop at 3 o'clock sharp, otherwise we won't have enough time for discussion, and we'd just like to let a little bit of time for the audience to ask questions to Frank. So who would like to start? Well, maybe I can actually start. If we come back to the last 800,000 of years, Frank, we see that Miss 11 really stand out.
Yeah.
Do you have an idea of why compared to the other interglacial, at least in the context, I would say, of the ice core timescales?
Yeah, I think it's also in other basins, but it's particularly known from the Pacific. You can see it even in like shallow seismic parasound data. You can see that stage 11, it's always a carbonate layer that is nearly reaching 100% of coccolith content. So there must be some extreme conditions, warm conditions. But the question if it's really so warm, so unusually warm, because the SST data that are available show that it's a bit warmer as always, but not